Hello everyone, welcome back to MAT052. This time we're going to be looking at finding critical values when we're in need to do the student's t-distribution. Last time we looked at finding a normal distribution, a value for the critical value from the normal distribution table. So that the normal distribution, the Z alpha 02 or the Z alpha critical values occur when either we're doing a confidence interval where the margin of error formula quotes Z alpha over 2. And also when we're doing hypothesis testing, when our test statistic formula, that's what we're usually given there, is a Z. So a Z test statistic, we have to have regions with the Z that separates the rejection region from the fail to reject. So here's going to be the T, so we're not going to get into those. We're having a confidence interval where our margin of error says T alpha over 2, or hypothesis testing when we've got a T value for the test statistic. It says T is equal to something. So we're going to be looking at finding those. There's a little difference between the normal and the student's T, and we'll kind of go back over that. I'm sure you've seen it in class, but I just want to review for you. Okay, so let's get started. Here is, put me down here. So critical values are used in both confidence intervals and hypothesis testing. In confidence intervals, we use critical values directly. They are always in the form T alpha over 2, and when I say directly, that's part of the margin of error formula. It'll say either T alpha over 2 or Z alpha over 2, and we're going to focus on T alpha over 2 this time. In hypothesis testing, we use critical values indirectly. So it's not part of the test statistic formula other than it says T is equal to. But what we need to do then is go over and look at each one. Does it tell us to do a left tail test, a right tail test, or two tail test? And in the situations we're saying that is a T value for the test statistic, we need to go to the student's T distribution table. Okay, so here's the T alpha over 2 for confidence intervals. This is what you'll always see kind of in the midst of these things. Here's a confidence interval for a mean standard deviation unknown, and it'll have X bar minus T alpha over 2. Here's the critical values, less than the mean, population mean, less than X bar plus T alpha over 2. And again, this is the critical value, and here's the standard error. So in general form, I'm going to go ahead and switch over, so just bear with me. Put this down here. So here, the general form again was X bar, or the P, plus or minus my margin of error. P. So if I did point estimate, so the most general form is point estimate plus or minus the margin of error, and this is based on, I've got an interval, the center of the interval is the point estimate, and then I'm going to do PE plus ME to get the inside, and then PE minus the margin of error to get that version. Let me kind of open this up a little bit so that we can see a little better here and here. Okay. So for this one, it just says that for mu sigma unknown, then I've got something that's looking like X bar plus or minus T alpha over 2. This is the critical value times S over the square root of N, and again, this is the standard error. So the general form is always here, PE plus or minus the critical value times a standard error formula. Okay. So for confidence intervals, we're always given the confidence level C again, and the area between negative T alpha over 2 and T alpha over 2, between that's the confidence level. So that's the area C in there. And then alpha is the total area outside. So this would be the C on the inside. And then the stuff on the outside is the alpha But in here, if I'm doing two tails, half of the area is on one side, half of the area of the alpha is on the other side. So we always do this to build in confidence, and this is just here. It's a very similar thing when I'm doing hypothesis testing two-tailed, except we're giving the alpha directly and we don't have to do this piece of it. I'm already given that. So again, this is the same thing that we did before. Alpha is just 1 minus c, so this would be the 0.80. And then if I'm doing alpha over 2 for the two-tailed, I'm dividing that by 2 to give me 0.10 for this. And for 90% confidence, I get my alpha 0.10, but alpha over 2 is that divided by 2. And again, anytime you see z alpha over 2, remember that you're dividing that alpha by the 2. So recall the format of the student's t-distribution table. That requires the degrees of freedom in there that as we go through, and we'll see that in just a second, but the degrees of freedom that we're going to use is always sample size minus 1. Other little difference, the area is always to the right as shown. Here, if you go to the top of A.3, it gives you the picture, and the area is to the right, and here's the T alpha that they're talking about on the inside. This could be a T alpha over 2, and it would be symmetric. So if you needed a left side, it's just symmetric over on the other side. It'd just be a negative value. Okay. So here, the area is also a difference. The area is at the top of the table. We'll go over that. And then the t-scores critical values are read from inside the table instead of being on the outside and top as we did for the normal distribution. So here's the student's t-distribution. This is kind of the picture that you'll see when you go to A.3. The area now is to the right instead of being always to the left when we're doing the normal distribution. And it says area and right tail. This is up at the top. So here is the value for alpha across here. Okay, if we were doing a two-tailed, I would use the same thing, give me the area and the right-tailed, and then I'm just going to do whatever the T alpha is plus or minus. Here are on the insides are the value of the T alpha / T alpha over 2 for the corresponding area in that right tail. Degrees of freedom are along the left, so I've got to find the degrees of freedom, and then I'll read over left to right to match up what the area is to get my T values. So let's do an example. So if I had an 80% confidence level, the sample size is 41. I would do, okay, alpha is my 1 minus c. There's my 0.20. I need an alpha over 2, so my area in the right side or the left side is 0.10. For a t, if I'm going to do t distribution, I need degrees of freedom. So the sample size was 41. 41 minus 1 is 40. So I start going to the table, A.3. Go down on the left side to match my degrees of freedom. Here, notice that this is 40. This is going 39 to 40. If I'd have had 45, I would still back up to 40. Okay, so this is the one all the way up until I get to 50, and then I start going to the next line. But now my alpha over 2, the area in the right tail, this is just the area in the right tail, 0.10 I'm looking for. This is corresponding to this, with my degrees of freedom 40, so it would be a 1.303 as my critical value. Okay. Now, depending on what I was doing, so this was confidence levels. So if I went here, and if I drew my picture, this would be the T alpha over 2. This would be the 1.303. And here would be negative 1.303. Now for confidence intervals, this is the only thing that I'm going to be concerned about because I need to use that and multiply times the standard error. So that would be that value, and that would give me the margin of error, just like that. Here again is a one for the 90% confidence. 90, 1 minus 0.90 gives me the alpha value of 0.10, and then alpha over 2 is my 0.05, the 0.10 divided by 2. My degrees of freedom would be 64. Notice that I don't have any entries between 60 and 80, so I always back up to 1. This opens it up. You see how these numbers are a little bigger, and that gives me a little more room for error. Okay. So 64, I go to my 60, and I'm looking for 0.05. This is the column with 0.05, so I would say 1.671 is our critical value. And again, in this case, that gives me two values just that I can mark it to keep up with it. 1.671, that's the value that I'm going to use in the formula. And this position right here is the negative 1.671, just like that. So for full alpha values, so for hypothesis testing, we're always given alpha, either for finding the rejection regions or comparing to the p-value. And again, we'll do p-values later. For two-tailed tests, we use the alpha over 2, just like we did in confidence intervals. But if we're doing left tails or right tails, we just use that full alpha. Okay, and they will give us the value of the alpha directly during hypothesis testing. That's one of the big differences. In confidence intervals, you're always given the confidence level. In hypothesis testing, you'll be saying, here is this alpha level. Here's the testing level, and that's the alpha. Okay, so critical region for the left. Here's my negative value for a T alpha. Separates the rejection region from fail to reject. Rejection region, fail to reject. But here I'm going to use, excuse me, alpha over 2. And then to the right tail, this will be a positive value. And my area to the right is alpha. So here's a left-tailed alpha. I'm given alpha is 0.05, sample size is 34. So I'm going to go here and I'm going to find the degrees of freedom 34. Alpha 0.05. Notice that this is in the right tail, but this is symmetric. So it's going to be the very same value, except it's going to be a positive here. So if I go down 34, alpha 0.05, it'll be 1.691 if that was to the right. It's going to be symmetric, so this is just negative 1.691. So this is what I've done here. Let me pull me up. Let's get rid of that. So here I've got a left-tailed with area 0.05, alpha is 0.05, but I'm using this to get the value. Since it's only got half the chart, it doesn't give me the full thing in the area, but it's symmetric, so I just go to the 0.05 degrees of freedom and I say this would be 1.691, so this would be negative 1.691. If this was here to the 0.05 to the right, this would be the very same symmetry and alpha 0.05 to the left, except it's just a negative number, and I just used the negative version. So here I need this because now I'm going to use rejection region, fail to reject, and who am I rejecting? Always H0, or fail to reject. So what about if it was a right-tailed? I'm going to do the very same thing, except this will be given to me directly. I don't need this stuff anymore. I need the right-tailed. I could have just drawn this over. Right-tailed, I need that value. Here's the alpha 0.05 to the right. And this gives me that directly. So the very same thing, everything was the same. I would just use the positive 1.695. And again, that's the zero value at that hump when I'm plotting. For a two-tailed, I need to divide by 2 to start with. So if I was given alpha as 0.10, this is given for hypothesis testing, I do the very same thing I did for confidence. I divide by 2. Use degrees of freedom. So let's say, example, our degrees of freedom was 220. It maxes out. If we go through, it maxes out at 200. And if it's close to a little bit more than 200, I need to back up. If it's a little less, I go to 100. But if it's very big, 1,000, I would just use my Z table. Okay, I could just go to the Z. And it's kind of given, here's the values for that. 0.05, 200, 1.653, but I'm doing a two-tailed. I'm doing a two-tailed hypothesis test. This is failed to reject region, failed to reject A0, rejection region A0, rejection region. I got two rejection regions. So later when I'm doing the test statistics and I plot from the sample, wherever I land, that'll tell me. But here's the breakpoint that I can use to say, am I further to the right or in here? Okay, so those critical values for this particular picture would be, if I read it over 200.05 to 1.653, and again, it's a two-tailed, and this would be the minus 1.653. Okay, so that's the basics of it. Let's go look at the worksheet. If I go through here, I'm doing the very same thing that I did with the normal distribution, finding critical values. But here I'm telling you that the sigma is unknown, sample size is 33, what are the degrees of freedom, that narrows it down for you. If I don't know the population sigma, I've got to use the T alpha over 2 S times the square root of n. So for like number 1, this is what I'm doing. I've got to do the critical value for 90% confidence interval for the mean. So I've got this, and for this, for sigma unknown, I've got T alpha over 2 times S square root of n. That says I didn't know the sigma, the population sigma. I have to use that. Okay. So the degrees of freedom here, if the sample size was 33, I would do the 32 and then do just like I went through and stepped through. Okay. First two are confidence intervals. Here's some hypothesis testing. Do those critical values that separates the rejection from the failed to reject regions in a left tail hypothesis test. This should have been unknown. Do that with the sigma unknown. Degrees of freedom 72. Unknown. Degrees of freedom of 72. These all should have been unknown. I should have changed them, but I didn't. But that should get you from where you was. Just correct it in your paper for me. That'll let me know that you knew what you were doing. Okay, hope that helps, and we'll see you next time.